Wait, did it start?
Did it?
Yes, it is. It's recording. Okay. All right, so we are currently recording. And we're looking at Newton's law of cooling today. So we have actually done some problems with Newton's law of cooling, but today that's our total focus. So let's make sure we understand each and every part of this formula. T of T. What does this part mean in the formula? T of T represents the temperature of an object with respect to time. So as time passes, what happens to the temperature of the object? T of E is the temperature of the environment. So if the environment was this classroom, the temperature is currently 73.4 degrees. That's the temperature of the environment. Now, if I had anything in here, like my cup of coffee right here, okay, would the temperature of this cup of coffee ever fall below the temperature of the room?
No.
No. Okay, smart. So the temperature of the room might act as what in a graph? Now, it can actually equal, but it does kind of work like an asymptote. It gets there and it stops. Cool. All right. Okay. T naught. T sub 0. T naught. Naught. I can't say that correctly. But that means nothing. Temperature at time 0 is the initial temperature of the object. Lowercase t represents time, and k is our favorite. That's our constant. That's the one we have to solve for first, isn't it?
Yes.
Before we can do anything else. So in this example, we're starting off with a egg that's just been boiled. So now we have a hard-boiled egg. And the current temperature of the hard-boiled egg, it must have just come out of that water, right? 96 degrees Celsius. That's pretty hot, isn't it? You should use tongs. All right, now, this egg is now being placed into a 16 degrees Celsius water to cool. Water. 4 minutes later, the temperature of the egg is now 45 degrees Celsius. When will the egg reach 20 degrees? So when you get a problem like this, first you have to understand, how do all of these numbers relate to this stuff and the formula? So let's go through. The temperature of the hard-boiled egg. Ooh, I like it. It's the temperature of our hard-boiled egg, which is our initial temperature, T naught, and that initial temperature is what? 96 degrees Celsius. Beautiful. Okay, we also have the temperature of the water.
Environment.
So, in our case, that water is its environment. We're placing the egg into 16 degree environment. Okay, and for us, the only time we have right here is it tells us 4 minutes later. So 4 minutes later, in our case, is going to represent our time. And we know it's measured in minutes. Okay, and the last part we get from this very first sentence is this. The temperature, the final temperature of the egg. Well, basically, when will the temperature of the egg reach 45 degrees? So what is that 45 degrees Celsius in terms of this formula?
The temperature with respect to time.
Very good. The temperature with respect to time.
That's what I said.
Okay, good. We've got everything but K.
Yeah.
So we can solve for K. So let's take all these numbers and plug them in. Let's see how that looks. So we get 45 equals, because this is the temperature we reach after 4 minutes. 45 equals TE, which is 16, plus T naught minus TE, so that's going to be 96 minus 16, e to the negative k, t. And the time that has passed in this situation is 4 minutes. So we're going to do a little algebraic manipulation, and eventually we're going to solve for k. So the first thing we would do is get 80. Then we would subtract the 16.
Then you get really upset because it's not an E. Well, it is.
It is E, but it's not just E yet. So we still have to do some more work. You're right. You should not be happy yet.
Never happy.
Well, then this works out well for you, Mary.
Divide by 80.
Okay, so we're going to divide by 80. Love it. When we divide by 80, now what we have done is we have created an exponential equation. And we can solve for the exponent of this exponential equation by doing what? Taking the natural log of both sides. Beautiful. Okay. We love taking the natural log of E because when we bring that exponent out and it's multiplied times the natural log of E, what is the value of the natural log of E? 1. And so we can kind of ignore that because multiplying by 1 doesn't change anything. So our last step is to divide by -4. And we have just found a beautiful exact value for K. And we will always use a beautiful exact value. So this is like step 1. Okay, it's a lot of steps in step 1, isn't it? Let's call it part 1.
Wait, it's only step 1 on my room one.
Wait, Miss Willoughby.
That's part 1.
Why isn't it ln of 29 over negative 320?
What?
We don't find K.
Like with it, because why? I mean, why isn't
multiply negative 4 times?
no? Why isn't the 80 multiplied?
We have to get the equation in exponential form where we have just a base raised to an exponent equals an answer. We can't have something multiplied out in front if we're going to take the natural log of both sides. We have to have just E to the sum power equals something.
Yeah, I got that. I'm sorry. Like the very last line, like k equals. Why isn't
Okay.
ln of 29 over 80 times negative 4?
Because to solve for K over here, it was -4 times K, so we had to divide by -4.
Right, but if 80 is the
Because
denominator.
80 is in the log and negative 4 isn't.
Okay. She actually did a really good job of answering that question.
Sarah Grace Biddle, not going to become a teacher.
No, that's okay. All right. So this 80 is not the number 80. It's not 80 divided by 4. This 80 is part of this natural log.
I wish I knew that.
All right.
Like, after you're done-
Part 2.
Oh, that's not interesting. You guys already done it.
Part 2. So after we find K, just like we had to do on that half-life formula on the quiz, we had to find K first, didn't we? Yeah. We should have. So if we found K first, then we can answer the question. When will the egg reach 20 degrees? So now we have a new T of T. Okay? Our T of T is 20.
This is the ugliest number I have ever seen.
And what we want is the approximate time. When does it hit 20? So, we know everything we need to know. We know T of T is 20. The environment was 16. The initial was 96. The K is this beautiful number. Now, the cool part about this is, in the formula, it's negative K. And then K is negative. So what happens to a negative and a negative?
Cancel.
They cancel. So I'm going to put them right here because every time people ask me what happens when I don't. So a negative and a negative cancel. And so basically we do the exact same process except we're solving for T instead of K. So we're going to subtract 16 and we get 4 equals 80 E, and And the negatives are going to cancel, so now I'm not going to write all the negatives. I'm just going to write ln of 29/80ths over 4 times t. I'm going to divide by 80 and get excited because this is exact. Of course, that excitement doesn't last long because I look at this exponent and it scares me. But I keep going.
Somebody gonna write a children's book about like somebody going through like all these math
A
problems.
math
and
problem.
their
Ooh!
Actual fear.
I would buy it.
I know you would. This will be. I'm specifically selling to a market of math teacher
I like
parents.
it. I like it.
One could say that math and the level that you learn is comparable to Dante's Inferno.
Yes,
Yes.
one could. One did.
It gets progressively worse.
All right.
No math.
So I'm taking the natural log of both sides because I got it down to exponential form.
You guys are talking about that
We called our class.
You guys are talking on a recording that'll be posted to the internet for the world.
I'm complimenting her.
Okay.
If you're watching this,
So we have this fraction. It's ugly. You guys are not good at putting parentheses where they need to go when you put stuff in the calculator. So just multiply by the reciprocal. Well, you're not. I mean, I even wrote it on the board the other day where all the parentheses go. And then people kept bringing me their quizzes going, this doesn't look right. It doesn't look right to me either. So what we could punch in is 4 times ln of 0.5. Enter. Divide by natural log of 29/80ths. Or, if you're good with a calculator, you could have done natural log of 0.5 divided by, big parentheses, natural log of 29/80ths, close your little parentheses, divided by 4. Either way, if you enter it accurately, you should get approximately 11.81 minutes later.
Yay.
My egg is now the temperature I want it to be.
They should have like a semester.
Yes, sir.
I got 11.79.
Yeah, they
Would that
really
be kind
should.
of wrong?
No one really knows how to use all of it.
Yeah, and you used all of this?
Oh wait, I think I see what I did.
Okay.
Okay.
I'm pretty sure if you were to apply this to real life, by the time you did all this math to find out how long your egg would be cool, your egg would be cool. And then you just really.
Okay, so nobody sitting in their own kitchen boiling an egg would ever do this.
The more you
But,
Say that.
but, if you worked for a company and your job was to determine how long the eggs need to sit in this water before we can put them in the plastic packaging so that they don't leach any of the plastic at a certain temperature, then you could mathematically determine this, and then you can set the schedule.
They already put that formula, it's already figured out.
Or to calculate like how long you need to let something like sit before you eat it. Like,
You could do that, yes.
I'm like, I'm just so
Wait, no, I was just asking.
cold like black.
No, it
If we work for McDonald's corporate and we're setting the timer for how long we leave the fries.
No, I'm 93% sure she doesn't know.
And it's different.
I didn't say loud enough.
This will be.
Why did you rip my paper?
I'm so weird. I promise. You like walked right here. I'm like, Mr. Levy, may use the restroom.
That still exists. It's amazing.
Okay, number 1 is review. It's not Newton's law of cooling. It's just can we use the decay formula with a base of E? So number 1 was not not new at all. You just had to go through, you had to read. You're going, ooh, I'm starting off with 40,000 bacteria. No, I started off with 10,000, ended up with 40,000. That change happened over how many hours? 2, because from 3 hours to 5 hours is 2. And then if we solve for K, then we can determine what the initial population of bacteria was. So this is kind of a cool problem where they don't give us P0. And sometimes we're not given the initial, and we have to work backwards to it. But if I give you a problem where I don't give you the initial population or the initial temperature, I'm going to give you enough information to work backwards to it. So this is an example of that. So what we kind of pretended like in this problem was that 3 hours later is actually times 0, didn't we? So 5 hours later, the 40,000 would not be 5 hours later. It would actually be 2, because that's the difference between the 3 and the 5. So sometimes we kind of have to play with it to find our constant, and then we can work backwards and find our initials. Okay, so that was just helping you look at that in a different way, knowing that we don't always have to be given that initial if we're given 2 other pieces of information that are valid.
Did Doug just leave?
Yes. All right, you have the rest of class to work on 2 through 5. My answer keys up here on the overhead. Good luck. Oh, I'm actually posting my answer keys for you to look at so that tomorrow you can be successful in class and get that finished during a class period.
Wait, so this is like, we work on